Today we are going to learn about a number that's called E. It's kind of strange to call a number a letter, a number, but there's a special number that was given the name E. It's kind of like pi is a really special number, and we just gave it this symbol pi. Pi is actually a letter. It's just a Greek letter for this particular number, which is a very special number. The person who discovered it was named Euler, which is spelled E-U-L-E-R. So he named this number after himself, Euler's number. And so we just use the letter E to represent this number. The definition of E is very overwhelming. This is a notation that if you go into calculus, you'll learn, but it's actually fairly simple to explain what's going on here. What this says at the bottom here is n is heading to infinity. That means n is getting really, 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 really big. Okay? So if you start out with n not so big, and say n is like 1, and you plug this in, you get 2. Right? As n becomes absolutely enormous, something like that. Okay, but even bigger, right? Because we're talking about like infinity. So as n becomes really, 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 really big, we get this number. Okay? This is a special number like pi. So pi is what we call an irrational number. It means it can't be written as a fraction because it's a decimal that goes on forever and ever and ever without ever starting to repeat itself. There's no pattern to its digits. E is the same way. It goes on forever and ever and ever without ever starting to repeat itself with no pattern in its digits. So it's about 2.7 is what we'll use to kind of represent it, or 2.72, but it's a very special number like pi. Since it's just a number, it's going to behave like any other number or any other variable. So we can apply all the same types of rules to it. So if this were like x to the third, x to the fourth, what would we do with those exponents? Add them. We're going to do that here too. So it's just going to be e to the 7th. And we're just going to leave it right there without plugging it into our calculator. The calculators do have an E button on them that we can use. But unless your directions specifically say estimate or approximate or using a calculator, just leave it. Okay, just leave it at the E value unless the directions specifically tell you to take it to a calculator. So in this one, we can begin by dividing the coefficients, the numbers in the front. So we're going to get 2. And what do we do with those exponents when we're dividing?
Minus.
Subtract them. So e to the third over e to the second. 3 minus 2 just gives e to the first, or just e. If you write the e to the first, that's fine, but we don't really need an exponent of 1. What do we do with a power outside of parentheses? We need to give it to everything inside. Everything inside of here needs to be squared. So 3 squared. And then what do we do with power to a power? Multiply them. So that's going to be e to the negative 8x. What is 3 squared? 9. And what do we do with negative exponents? That's going to give you a hint, right? We're going to put them onto the bottom of a fraction. Okay, so all the properties that we learned earlier this year that apply to variables or other numbers apply to E as well, because E is just a number. It's a special number, but it's just a number. Our next problem wants us to approximate this on a calculator, so I'm going to go ahead and get the calculator up and show you where to find the E button. Okay, so there are 2 places to find an E button on the calculator. One of them is right here above the division, that if you press second and then the division button, it brings up the E. And then the problem said e to the power of 2 or e squared, so you can type in power of 2 and get it there. Another place to find the E button, which I find is usually the more convenient location, is over here next to the 4, above this button that says LN. We'll talk about what LN is in a couple of lessons. But up here, there's one that says e to the x. And I find that to just be a little bit more convenient because most of the time when we work with e's, they're going to be raised to some power. So this kind of takes care of finding your e and finding the power. So it's kind of like hitting two buttons with just hitting one. So then I could do e to the power of 2, close off this parentheses, and we get the same exact thing. So it doesn't matter which of those buttons you go to. I typically go to the power one just because then I don't have to press the power button also.
On mine, I have a Casio, and I can't find the first one. Like, it only is the e to the power.
That's fine. So then if you ever needed to know what just e is, just put in a power of 1.
Oh, okay.
Yep. I pretty much always go to the e to the x. And I think it's kind of silly that they actually bothered to put them both on here because you don't really need both of them. They just did for some reason. So the next problem in the notes then asks you to find e to the negative 0.06. So I'm going to go e to the, when you do a negative, make sure you do the little negative, not the subtraction, because we're not subtracting, we just have a negative number, 0.06. And then again, at just about 1 or 2 decimal places, so about 0.94 is good. Okay. So our next problem one is to graph with an e function. So we've learned 2 different types of exponential graphs so far. This is going to be an exponential graph because it has an x up in the exponent spot. So this is going to be an exponential graph. So then the question is it going to be a growth or a decay? And there is one group of your homework problems that just asks you, is it growth or decay? You don't have to graph it to be able to tell that. We can just look at the equation. So now this is asking a lot of you to remember this after about 2 weeks, but how can we tell?
Oh, do you have batteries or another
I don't.
calculator?
I don't have any batteries.
Another calculator.
How can we tell if it is a growth or a decay?
Positive exponent.
Positive exponent will make a growth. So a negative exponent would make a decay. Or there was one other way. Something with a base. If the base is between 0 and 1, so a decimal or a fraction between 0 and 1 as the base number, then that will make a decay. So the base here is e. And e is about 2.7, so our base is bigger than 1. So that means the only way we can have a decay function, if there's an e in it, is if that exponent is negative. Okay, and here our exponent is positive, so this is going to be a growth function. Right, so one group of your homework problems will just specifically ask you, is it decay or is it growth? Look at that exponent. A positive exponent is going to create a growth, a negative exponent will create a decay. Okay, so to graph an exponential function with an e in it, we're going to do so with an xy chart, just like we've been doing when they didn't have e's in it. I'm going to use a negative 1, 0, 1, and 2 again as our x's. And then you're really just going to need to type this whole thing into the calculator. So I don't expect you to be able to evaluate e things by hand with that gross decimal. So what you're going to do is just type them each into the calculator. So a little calculator trick for you that could make this maybe a little bit more quick to type these all in is, so our equation was 2 e to the 0.75 times x. So the first x I chose was negative 1, so I'm going to put in a negative 1. Close it off. And hit enter. And then you really only need to go to 1 decimal place on this because you're putting them onto a graph. So as you graph the point, 0.9 or 0.94, you're not going to be able to tell a difference on your graph. So really just going to 1 decimal point is fine on this. Now, we need to type this in for each of the x values that we chose, which could be a little bit annoying. A calculator shortcut for you, if you want to bring up the exact last thing that you typed in, just press second and then enter, and it brings it all back. So then I can just go back and change that negative 1 to a 0 for the next thing to evaluate. I hit enter and it gives me 2. Then I press second, enter, and it brings it all back. And I can go change it to a 1. And again, just go about 1 decimal place, so about 4.2. Second, enter, it brings it all back. And I can go and change that to a 2. And so I get about 9. Okay? So we get our XY chart that way, so that we can then create our graph. So in that XY chart, when X was -1, I got about 0.9. When X was 0, I got 2. When X was 1, I got about 4.2. And then 9 is somewhere up there. So I'm going to connect those dots. And we see the same type of exponential growth function that we've been seeing. Okay? We said the bigger the base, the steeper the curve is going to be. And when we're using a base of E, E is between 2 and 3, it's about 2.7. So it's a pretty big size base. We're going to expect to see a fairly sharp turn in these functions. Domain and range. Domain for any type of exponential function, no matter what the base is, no matter if it's growth, decay, no matter what, exponentials, domain is all real. So you can plug in any x you want. Range is limited though, because there's an asymptote here that this graph is never going to cross. Range is a y value. Is it going to be greater or less? Greater or less on this one? Greater, because it's above, and what is it above? 0. This next one has some shifting involved in it. So the first thing we're going to do is take care of the shifting that occurs in this graph. So what does the -2 up with the x do? The x minus 2. How does that change our graph?
To the left.
Close.
To the right.
The right.
Oh.
It's a sideways, but it goes backwards when we have a sideways. And what's the +1 do? Up 1. So we're going to go to the right 2 and up 1 to kind of recenter our graph. Then, when we make our chart, as we have for the other ones, we're going to deal with just the stuff we haven't dealt with. So we get to ignore the -2 and the +1 because we took care of those by recentering the graph. So again, you would plug these into your calculator. So you do e to the -0.1, which is about 1.6. E to the 0 is 1. Anything to the 0 power is 1, except 0, which is a whole special thing. E to the first. Oh, you know what? I'm looking at a different problem. That 1.6 is not true. My notes have a different problem on them than yours. Let's try this again. Oh, that calculator's good. E to the -1 is 0.4. Okay. E to the 0, 1. E to the first is about 2.7, and e squared is about 7.4. So we're going to plot these, but since we were plugging them into an altered equation, not the original equation, we need to plug them into the altered axes, or where we recentered our graph. So from where those new axes meet, or the dotted lines, we're going to go back 1 and up 0.4, and over 0 up 1, over 1 up 2.7. I'm not going to do the 7.4. And we see a growth. We should expect a growth on this one because the exponent is positive. Okay? It was just a plain x, so it's like a positive 1x. Domain and range. Domain will be all reals. Range will be limited. Y is it going to be greater or less? Greater because it's above, and what is it above? 1.
0. 1.
Okay. 1 because we had the shift. Okay. was looking at an application that students typically enjoy because it has to do with money. So a few lessons back in lesson 1, we had this big messy formula, and I told you didn't need to worry about memorizing this formula. And this was the formula that we use to figure out how much money we have in the bank when they compound our interest. And compounding interest is when they give you some interest, and then the next time they go to give you more interest, they give it to you not only on what you put in, which is called the principal, but also on the interest they already gave you. Okay? So let's say you put in $100. At the end of the year, they gave you another $5. Then the next time they go to figure out the interest, they're going to figure it on $105, not just your original $100. So that's a good thing. Your money's going to grow faster that way. In this formula, P was the principal, or how much money you put in. R was the interest rate. N was the number of times they compounded it in a year. So were they giving you interest just once a year, or every quarter, or every month, or every day? And we learned the more often they compound, the better it is for you. You get money faster that way. In reality, what most financial institutions do is something called continuous compounding. That means they are constantly figuring out your money. Now, they're not constantly putting it into the account because it would be like fractions of pennies. So they're still only going to actually give you the money every so often, but they're figuring the interest constantly. And this is the best case scenario for you. Another really nice thing about this is when they do that, this big messy formula simplifies down to having an E in it instead of all that 1 and rate over stuff, because that looks a lot like the formula for E anyway. We call this our PERT formula because that's what it spells. And this is the formula that we use in financial to figure out when our money is compounded continuously, how much money do we have after a given time. So in this formula, P is our principal, or how much money we put in the bank. E is that number E. R is our interest rate. And T is the number of years that we leave our money sitting there. Okay, time is always measured in years in this formula. So if we deposit $1,000 into an account, that's our principal, that pays 8% interest, that's our rate. What is the balance after 1 year? That is our time. So our equation is amount is equal to PERT, P-E to the power of RT. You do need to memorize this formula. You do not need to memorize the really messy version of it, but this one you do because 2 reasons. It's a lot cleaner, so I think you can handle it, and it's more realistic because this is really what most financial institutions do and not the other one. So amount is equal to, P is 1,000, E, rate is 0.08 times time is 1. Make sure you put parentheses around that when you put it in your calculator. When you do the E to the button, it automatically opens up parentheses, so that's a good thing, but make sure that you do keep those parentheses there and close it off after the time. It can make a difference because we want that all to be up in the exponent. Make sure also that you remember to turn your percent rate into a decimal. Okay, don't plug in an actual 8. I would love to store money with you if that's how you're going to figure out interest, because you will get insane answers if you forget to change your rate to a decimal. So make sure that you figure that as a decimal. And you plug that in, you get $1,083.29. So after 1 year of just letting your money sit there, you earned $83.29. For the next one, our principal is $1,500. Our rate is 0.075, and our time is 1 year again. So we plug that in the calculator, making sure to use those parentheses, and we get 1683. So after 1 year of just letting our money sit there, we earned $116.83. It's not a bad deal. Questions? 8.3 assignment for tonight.